All right. Okay. So guys, this is real analysis class one. Um, the introduction to real analysis one. So this class is specifically for those in um, year two, year three, year four, and so on in the field of mathematics and engineering. So in this video, will be this video is split into various parts. So the first part of this video is the um, the bound of real numbers. So as you can see, the second part we're dealing with field, the other field, the least upper bound, and the greatest lower bound. While the second part of this video will be treating sequences. We'll be treating what sequences as the second part of the video, where we'll talk about we will treat the bound sequence, the monotonic sequence, the Cauchy sequence. Then we'll talk about some proofs, some theorems, some lemma, and so on. Of course, in this video, the first part of the video, we'll talk about field as well. Now, if this is your first class in an analysis class, I would like to make an introduction to some of the parameters we use when it comes to what real analysis, some of the symbols that we use. Now, the first symbol over here that we use is the there exists. Is the there exists. Now, this is there exists. There exists. Now, how do we use the there exists symbol? Now, for example, let's say you have a set of real numbers. For example, let's say you have 1, 2, 3. Let's say some set of real numbers. Now we can say that 1 is a member of real numbers. We can say that there exists a real number. Do you understand? There exists a real number. So this is some of the ways we use the there exists symbol. Of course, we can also say there exists 1. Or if you want to write this is there exists a unique element. There exists a unique element. If you want to write this like that. Now the second value, the second symbol we have is the for all. For all. Now the for all symbol is mostly used in binary operation or in closure properties, in stating axioms and theorems in mathematics or in real analysis. Now the next one we have is such that. You can see such that. In most cases we write our such that like this in real analysis. Now we have the set of natural numbers. The set of natural numbers are 1, 2, 3. These are set of natural numbers. While the set of real numbers ranges from minus infinity to positive infinity. So these are set of what? Real numbers. Now, one relationship about the natural numbers and the real numbers is that the natural numbers, they are subsets of what? Of the real numbers. That is, they are contained in what? In the real numbers. So you see, we have 0 is a member of the 0, 1, 2, 3. These are real numbers. Another a typical example of real numbers are 0, 1, 2, 3. So comparing this what we have here and what we have here, you can see that we have 1, 2, 3 here, we have 0, 1, 2, 3 here. So we can say that n is a subset of r because 1, 2, 3 is contained in this place. So we can say that n is a subset of r. So the set of natural number is contained in real numbers. Now we also have other type of number like the 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 integers or the rational numbers. So the rational number is known as r. So you can see there is known as q. The symbol is q. This is rational number. These are numbers that are written in form of fraction like 1 over 2, 2 over 3, and so on. These are rational numbers. We have irrational numbers. Examples of irrational numbers are pi, e, and square root of 5, square root of 7, and so on. All these are irrational numbers. And one thing you should know is that all of these numbers, this one is integers. The set of integers also ranges from minus infinity to positive infinity. So all of these numbers are contained in the complex number. So the complex number, this one here means there exists a unique element. I explained it earlier why this one is a complex number. A complex number has both a real number and a complex part. So we can say that the set of natural numbers is contained in the set of integers. Integers is contained in the set of real numbers. Real numbers is contained in the set of complex numbers. So all of these numbers are contained in the complex number. Now most people believe that the real number is the father of the all numbers. Meanwhile, the complex number has two parts. It has an imaginary part and a complex part. So A is the imaginary part, which is real. Sorry, A is the real part, while this part is the imaginary part. So you can see that a complex number has an imaginary part. So that's why you have this statement that natural numbers are contained in Z are contained in R, and R is contained in complex numbers. So these are some of the relationships surrounding this problem. So the concept of real number system is highly appreciated whenever you want to start your journey um, in real analysis. Now, one thing that you must also take note of when dealing with real analysis is the binary operation. Binary operation. Now, one important aspect that must be dealt with is the closure property, closure aspect. Now we have what we call the commutative law, the associative law, the identity law, the inverse law, and so on, and the closure law or the closure property. Now the closure property is mostly used in reanalysis. When we say something is closed, what we mean is that let's say you have let's pick the set of natural number. For example, natural numbers start from 1, 2, 3. So if you pick two elements from this place and you add them together, let's say 1 plus 2. 1 plus 2 is the same thing as 3. But this same 3 that we have belongs to or is a member of natural numbers. Do you understand? So it simply means that 3 is closed under the set of what? Addition. So similarly, if you say 1 times 2, 1 times 2 is the same thing as 2, but 2 is a member of natural numbers. So we say that 2 2 is closed under the set of multiplication. Is closed under the set of what multiplication. Now, in order to aid your knowledge in real analysis, let me give you 3 different topics you need to review your knowledge on before delving into real analysis. Number one topic is sets. You need to know what set is. Number 2 topic is the real number system. Number 3 topic is binary operation. So if you want to build your knowledge in real numbers, in real analysis, you need to review these basic things that you have ideas about: sets, the real number system, and binary operation. So moving down to the definition of a field. Now, when we say field simply means you can bring in the concept of a football field. Now, before you can say this place is a football field, it simply means that you must have 11 players and a goalkeeper, and you must have a coach and every other things that must be satisfied before you can say, okay, this is a football field. Likewise, the field in real analysis. So, as this axiom, this one, and this one, the remaining one, A inverse equals to A inverse A. This is the last one. All of these axioms must be obeyed before you can say that this parameter is it is a field. So this one is commutative law. This one is commutative. Commutative means that when you add 1 plus 2, 1 plus 2 is the same thing as 2 plus 1. That is commutative. Do you understand? That's commutative. This one is associative. Associative law. So associative law is A plus B plus C. Now, at the end of the day, if you state all of this individually, if you state the first one, it is a must that you put for every value of A, B in F, because we are dealing with F. Now, what is the field? The field has 2 operations. It has 2 binary operations. It has the addition and it has the multiplication. So you can see the first one we have is addition. So if you pick 2 elements from the field, the elements of the field are, look up, the members that we have in the field, they are A, B, and C. These are the 3 elements you have in the field. Now, if you pick 2 elements together and you add A plus B, is the same thing as B plus A. It means that is associative. That is commutative. If you decide to pick the 3 of them, it is associative. Now, if you add A with any identity, 0 is called the additive identity, as the number 3 is called the identity, right? So A plus 0 is the same thing as 0 plus A. 1 plus 0 is the same thing as 0 plus 1. 2 plus 0 is 2. 3 plus 0 is 3. 4 plus 0 is 4. So the 0 there means an additive identity. Now, the next one we have is the additive inverse. A plus minus A is the same thing as minus A plus A. This is what we refer to as the additive inverse. So the additive inverse for 2 is minus 2. The additive inverse for 3 is minus 3. So all of this is always equals to 0. This one, all of this here is always equals to 0. Now notice that everything we'll be stating so far is based on the addition and the inverse of the addition. So that is why the first one is obeyed by plus, while the second one is obeyed by what? Multiplication. So this one now is the associative law for multiplication. This one over here is referred to as the identity additive, the multiplicative identity. So 2 times 1 2, 3 times 1 3, 4 times 1 4, 5 times 1 5. So the one there is called the multiplicative identity. Now this last one is what we refer to as the distributive law. So we have AB plus C. When you distribute it, you have AB plus what? AC. Now there is something called the left distributive law and the right distributive law. So check out my video on introduction to algebra, where all of this concept is explained. Introduction to algebra. Check my videos on there. So I stated there. Now the last axiom that must be obeyed before you can say that all of this is a set is the multiplicative inverse. A inverse equals to A inverse A. So this is the last law that must be obeyed. Now there's something called the abelian group. The abelian group is what we refer to as a commutative group. Any group that is commutative is abelian. For example, this one, the first one over here is abelian. This one too is abelian. So any commutative group is what is an abelian group. So check out my videos on algebra too, where I explain the concept of groups and rings, right? So check that out. So now we are delving into real analysis class fully. So the first thing you come across when it comes to real analysis class is what referred to as an upper bound. An upper bound. Then we talk about the least upper bound, the lower bound, the greatest lower bound, and the like. So let me quickly give you a scenario of what a lower bound and upper bound is. I'll just place two examples and you just tell me what it is. For example, if you have 1, 2, up to 10, the first one is the upper bound. Sorry, the first one is the lower bound, while this one is the upper bound. This is the lower bound, while this one is what? The upper bound. You understand? So let me give you another scenario. Let's say you have 1 over 2, 1 over 2. Let me clean this. Let's say you have 1 over 2 down to 0. You have 1 over 2 here down to what? 0. So 1 over 2 is 0.5. So 0.5 is the upper bound, while this one here is called the lower bound. Please take note of the difference. This one here is the upper bound, while this one is the lower bound. So now, but checking out what the definition is, it is advisable to know the definition, because most schools and most lecturers will demand your explanation or your definition of what an upper bound is. So you, of course, if you want to define this, you have let F be an ordered field. Now, when we say an ordered field, a typical example of an ordered field is a set of real numbers. Is a set of real numbers is an ordered field. So if you derive is ordered, if there exists a subset P of F such that A plus B is in P. So if you want to explain the concept of, let me clean some parts so I can explain some certain things. Okay, let me use there so we understand the concept of an order field very well. Let me keep it here. Okay, so when we say another field, let's say you have let F be another field, and let F, if field F is ordered if there exists a subset P, if there exists a subset P of F such that A plus B is a P. So let's say you have a value of P. Let's say your P is equals to have some elements A and B, for example. Now, and you have a field. Now, this same field has its own elements. Now, but these elements that we have of F has A, B, and C. You understand? So if that should be the case, we can say that P is a subset of what? Of F. So this is what we refer to as what? As an order field. This is what we refer to what? As an order field. You understand? So that is an order field. So you can see that for every value of A plus B, when you take the addition, A plus B must also be in P for every value of what? A comma B in what? P. This is what we refer to as what? As an ordered field. So let's move back to the definition of what we mean by upper bound. So I already explained what is an upper bound. So by the definition, you see that before you can even list the definition of an upper bound, we have what we refer to as an ordered field. So a field must be ordered before you can say that it is an upper bound. And when defining an upper bound, you can see that let S, capital letter S, be a non-empty subset of F. So S is a non-empty subset of F. So and of an element F, and B is an element in F. So if B is an element in F, so B is called an upper bound for the set S if and only if S is less than what? B. Now this S that we have is a small letter, is an element. It is different from this capital letter S that we have. Do you understand? So it simply means that this S that you have is a member of this capital letter S that you have. So this S must always is less than B if capital letter S is a subset of F. So if this condition is satisfied, then we say that it is what? It is an upper bound. So least upper bound, you already know what an upper bound is. So least upper bound is the smallest upper bound. Why the same thing for the lower bound too. The upper bound is the greatest lower bound. So the opposite of the lower bound of the upper bound is the lower bound. So in this case now you can see that A is in F. Do you understand? A is an element in F. It's called the lower bound for the set S if A is less than what? S. But this one now, it is when S is less than B. But for this one, it is when A is less than S. So take note of those definitions and those symbols whenever you are giving out the definition of least upper bound and greatest lower bound. So this is where we pause for this video. So in our next video, we'll be treating sequence where we'll discuss the monotonic sequence, the quartet sequence, and every other type of sequence with series of examples. So if you find this video helpful, kindly share across your colleagues and those that you feel it might be useful and helpful to. And don't forget to click on the subscribe button as well. Thank you.